Hello community, so great that you are back. We have 9 brand new papers for AI research. So let's try to explain AI from the ground up, but in a way that I can show you that those 9 papers perfectly will fit here our representation of AI. Because you are watching here the YouTube channel Discover AI, so let's have a look at the latest research. AI, we have here a vision language model or a large language model. We have our memory module. We have here an in-context learning prompt. Of course, we have tool use with our MCP protocol and agent-to-agent protocols. And you see, this is the simplest configuration currently we have as an agent. Now, those elements are of course connected because we hope that our LLM or vision language model has kind of an artificial intelligence, and this manifests itself in a reasoning capability. So whatever the LLM decides here to store in its memory, the particular form of knowledge or reasoning trajectory are now encoded here in a memory representation. The LLM also has, of course, the parametric knowledge. And you know, in our prompt, we have some in-context learning examples we can provide, and we have in-context learning. But of course, also this is connected via reasoning. So you see, we have some sites where the reasoning is the main element that we have to take care of. So let's have a look at those reasoning trajectories. Now, the first one you immediately understand, the reasoning is something that creates something, but also that protects something. Because if you have here a malicious prompt, you don't want that this knowledge enters here either your memory or your parametric knowledge of the LLM. Therefore, this is here kind of a cybersecurity gate here where the reasoning is here your main source of defense, that this is not entering here your core LLM. But of course, you also have in a reasoning trajectory, if you have chain of thought or anything like this, you also have multi-modal reasoning structures. Let's say the first here is for a large language model and the second is here for a vision language model. And you see if we choose here a specific textual token or visual token or any other kind of representation for our mathematical vector space, we do have multimodal token representation where the reasoning trajectory is now including all of these elements. And you immediately see, oh yeah, this is now getting interesting. So we have the same reasoning complexity to the memory, and we have, of course, this reasoning complexity to any new knowledge that is provided to us in a complex prompt. This is either DSPy or you just go with a normal prompt engineering, never mind. And of course, you have here reasoning process now here also if you want to use either some specific tools, a complete different set of other tools, how you will use these tools, at what time you will use the tool, for what complexity level you choose a particular tool. Reasoning is all over the place. If you want to learn more about this, I have a particular video that I tell you AI reasoning is primary textual, not really happening on the visual token complexities. But talking about learning, what you understand or what you know, we have an LLM, maybe this is an autoregressive model like a GPT-5 model or some Gemini model that you know. But you know that a transformer, especially here, not a complete T5 structure of a transformer, but also only a decoder part of the transformer is just one of the options we have. We also have here discrete diffusion models, or we have now continuous diffusion models. And those are different architecture for our VLM, particularly here the diffusion model started here out as a vision model, but now you can find them almost everywhere. So if you're really interested here in this particular architecture manifold, in this video I showed you here, we have diffusion models, we have flow-based models, we have energy-based models, and really in my last video I showed you here the results of MIT, Oxford and Harvard University. They build now here a bridge function between those two, and they call it an equilibrium matching. This is a revolutionary unification of these two kingdoms here, and this is if you want to have a deep dive. But as I told you, we have reasoning as the main object that we have to take care of. No? This protects us here, if you think about cybersecurity, but this allows us here a textual reasoning process, maybe a visual reasoning process, maybe an identification of the objects, or maybe a video generation. So reasoning you can have here in your LLM or VLM for planning the action the AI should perform. Or you have reasoning if you want to protect your system from some adversarial actions or some adversarial prompts. Or you have a reasoning complexity where the AI has to decide based on its training, hey, I want to connect now to some tools. I will use now maybe an MCP protocol. Maybe I'll just go for a simple API calling structure. And those tools, they include now a variety of options. You can go with a formal solver or you go for PDDL. And you know what? Those systems normally have no visual input. So you see, this will be here one of the papers I'm going to show you how we can extend this here to a multi-modality. But of course, coming back now and talking about a reasoning trajectory, you might now argue, okay, so we do have our AI complexity, which is great, but why do we need here suddenly formal solver? We do have AI systems, no? Well, it turns out that the AI is not able to have here the complete reasoning complexity in an AI system. So a good idea is to reduce the complexity that the AI system should perform, should calculate, and just outsource the most complex reasoning to deterministic systems that we already built for years. Let's say we have here a particular system that has A, B, C, D, E as a step, and we can be sure either you program this in a particular language, either you use C++ or Python or whatever you have, you know exactly the sequence how to calculate here, let's say a mathematical complexity. Then the AI is not calculating it within its neural network. That would be just a waste of energy, a waste of time, and a waste of precision. But we call here a tool, and this here we have deterministic tool use. Now let's say we have here the steps A, B, and C from our deterministic system. We have a result. Let's say you coded something. Now you have a result of the code. Ne? Now this result can now have a complexity of its own, either a semantic complexity or a visual complexity. And now what you do is you feed this back either directly into your prompt structure, if you have a particular format, JSON for example, or you say, I have to feed it back into the AI itself because this is the way to go. Now let's have a look at this in a little bit more precise way. So whenever you have a task, cybersecurity or logic task, you have an LLM or a VLM, whatever, you have an AI that is now using a particular, that decides the AI, I'm not going to do this myself, I'm going to outsource this high complexity that I as an AI cannot perform, and I build an AI system, for example, for a deterministic system. I have a tool use. Now let's say here in orange we have a PDDL. This is a planning domain definition language. This is an established package here, a formal language used in AI for specifying the planning and the schedule problems. It was developed here as a standard way to express elements necessary for automated planning system. So if we have this already coded, why not use it? So we have now more or less two basic options. No? Either we say, okay, we build an AI system, and if we have here our input layer that has a predefined input sequence for our deterministic PDDL structure, we say, great, the AI just learns which of those, let's say, reasoning elements or the complexity task elements are now transformed and mapped in a particular way so that we have now the correct input in all of these different input layers. Great. Then we have the external deterministic system that is coded, and guess what? We have an output. And as I already showed you, the output, whatever the complexity of the output may be, maybe a semantic complexity, maybe a visual complexity, we just feed now the result back into the AI. So the AI acts here as a translator. We get here a query complexity. The AI says, hey, I know I can connect to another deterministic tool. This tool calculates here the results. The result from the coding, let's say, is feedback to the AI, and the AI presents it now in a very specific wording, in a specific style, back to the human. This is what's happening today, and you see we reduce the complexity of the overall query, of the human query, because we say now the intelligence of the AI is just to understand what is the task, understand, do I have access to, 20, 50, 70 different tools on the internet in my corporate network? do I have access to all the possibilities to solve this? And yes, then I choose a particular tool. This is computed in a deterministic way, not in a probabilistic way. I get a result I can verify, and then I just have to transform it back. Of course, you have also the option to say, wait a minute, I can have another AI system, another agent, and now this AI here learns simply with a particular training set exactly what the deterministic code could do. So what we need a training data set. Let's say we have now 100,000 runs. We have the input and we have the output, and this is a pattern. Input-output pattern, simple. And the AI learns now this particular input-output pattern given enough training data, let's say 100,000 data sets. Maybe you need 1 million data set given the internal complexity of the deterministic system. And then your second option is, alternatively, you could build an AI system here. Then you have an agent here, you have another special scientific agent here, and then you feed it back. But why would you do this? Because you already reduced the complexity to a perfectly working deterministic system. Where do you need the core of the intelligence? Sometimes you just need the core of the intelligence in the translation, not in the calculation or in the performance itself. Since we talk here about training an AI system or training multiple AI system, let's come back. Because this is what you see in front of you is an AI and a simple agent. So we have to do the same here on our VLM. And the classical training steps you see here, pre-training, supervised fine-tuning, and reinforcement learning by verifiable reward systems. Now, just in one of my last videos, I showed you that if you have here a look of the illusion of intelligence AI, it is so important to integrate here already in the pre-training the reasoning traces. Otherwise, all of this here later will not be working. You can do supervised fine-tuning as much as you want. If the basic reasoning intelligence is not in your pre-training data set, where you learn here the basic functionality in AI, supervised fine-tuning will not help you and reinforcement learning will not help you. So currently, in the latest weeks, we understood how important here the injection here of the right complexity of your complexity task is in the pre-training data. Otherwise, supervised fine-tuning and RL will fail. Great. Now the next step is, and you see here, we go in a modular structure, we can reduce the complexity. Because now, and this is here latest publication by Apple says, hey, this is great, but if I just have not just only in-context learning in my prompt structure, but if I have my memory module for my agents, can I not have multiple memory modules? And in the simplest case, this is the memory model for theoretical physics, this is the memory module for chemistry, and this here is the memory model for medicine. So you see, given now the particularity of your query, of your task, the system might reason, the AI might reason, hey, I need, the mathematical memory and the medical memory to solve this. But for this, you have to train your AI system with, let's say, 100,000 of examples. So you have to predetermine already what kind of task you want to solve with this particular LLM or VLM or your agent. Otherwise, if you hope for a general intelligence, you will be disappointed. Okay, so you see, again, we reduce the complexity and separate it in multiple memory. Why? Modularity. Maybe we don't need physics, maybe we just need chemistry and medical, or we just need finance and economic memory structures, but not the rest. And of course, we can also add and modify the architecture of the LLM or of the VLM itself. Either with a VLM, we can go here with a vision transformer system, or we go with a normal non-T5 decoder transformer system like a GPT system. We can add layers to this structure. And you are familiar with PEFT-LoRa. This is a parameter-efficient fine-tuning structure where we have a low-rank adaptation mathematical algorithm for a simplification. And if you're really, and this is here done in the last weeks, you have a high complexity that our VLM or LLM cannot solve with its internal architecture, you can now put something on top with a high topological complexity. So for a very task-specific query, you just add here a complex topological space with the inherent training to be able to solve this task, and then you can just use a classical out-of-the-shelf LLM or VLM. So you see, again, modularity. We say, okay, we have a base model, we have it pre-trained, supervised, fine-tuned, reinforcement, learned, but then the complexity of the task suddenly changes from Monday to Tuesday. And you don't train the complete model. You just add specific layers or specific multi-head architectures that you decide are necessary, understanding here how this works in the architecture of your model. And then you train maybe only some lower models, or you only train some higher complexity topological elements to perform the task for you. So you see, modularity on this level, modularity on the architecture level, modularity here in the complete reasoning trajectory from in-context learning to tool use. And of course, we have to train the AI, the VLM, the LLM, how to use tools. And we have to provide thousands and thousands of examples how to use tools in a correct way with an input and output parameter, MCP. Hopefully there will be something that is much better than MCP coming out soon, agent-to-agent protocol, multi-agent system, and so on. So you see, this is currently what we have, reduced the complexity to the max. We build little agents for little low complexity tasks, and then we hope we bring everything back together. Yeah, talking about complexity, I personally use here the memory, the multiple memory modules here. If I encounter a sequential complexity in my task, if I encounter more or less a procedural complexity to solve, I go here for adding layers to the model. If you want to read more about this, I have a particular video here on a unified theory of agentic reasoning that is based on the latest research publication by UC Berkeley and NVIDIA. And here we talk about a geometric addition on the mathematical solutions. We not stay just in the pure mathematical space, but with the help of geometry, we can go so much further. Now, of course, we move here from a single agent here, and now imagine we add a second agent. And you might say, oh, wow, this is quite a dynamic system. So how do we connect here all those different pieces here to all these other wobbling pieces of a second agent? And I know you might say, hey, wait a minute, we have an agent-to-agent protocol from Google, or you have any other agent-to-agent protocol layers. Yeah. But this is not enough. We go now and we build now direct connection. We want to understand here an optimization procedure. And if everything is wobbling, you are really in for the latest research. Now, if you want to understand this, I have a video just days ago, whenever this video will go live. It's called AGI, Asymmetry Discovered. Here I show you the latest work from Harvard University, Stanford University, and MIT. What happens if agents disagree? This is an agent, and just saw here on the other side this agent. What if they do not agree? What if this VLM has a different opinion than this VLM or LLM? What the result here? I have even not integrated a RAG system. You see, the graph RAG system, there are so many possibilities that could go wrong. In each of these elements, you can have, for example, some illusions happening, some hallucination happening, some glitches in the system happening, and then our agents will not agree. They will heavily disagree. And we found a new mathematical solution, a methodology here, an AGI asymmetry, and how to solve this is explained in this video. And you might say, hey, but this video was now 2 or maybe even 3 days ago. What happened today? And you are absolutely right to ask this, because this is the channel Discover AI. So yes, absolutely. If we have this representation, I have chosen this representation because we have 9 new papers. And we will exactly now address here each of those elements and the interplay of those elements I hope I can explain here the content of the latest AI research to you in a very simple way. So even if you're not familiar with AI in detail, you understand the main idea and the basic modularity, the main tricks that we use currently to build the best AI systems in the world. And I say for this is now end of part 1. And if you're interested, hey, why not subscribe? And I see you in part 2.